Okay, so before we start, let's just address the elephant in the room right now. So this morning, are you like a millionaire right now? Today we have Ekin Karabulut. She's based in Munich right now, and Ekin is a data scientist. Previously, she is specialized in privacy implications of federated learning with deep neural networks. Through her journey, she focused on distributed training techniques and observed inefficiencies in GPU usage, both in research and industry settings. So as a data scientist at Run::AI, she thus established the AI Infrastructure Club on Discord to discuss everything GPU related, exchange ideas and support other members, and to get the most out of GPUs. And right now, she's exploring the efficient usage of large language models in production. I know you're very actively engaged in the Munich tech scene. You're also familiar with like the AI tinkers in Munich, I think. And you'll find her like participating in like different meetups, going to different communities, such as tum.ai, which I think you should touch on because I have no idea what that means. And then you also serve as a team lead and a board member at tum.ai. And like most guests in our webinar, I asked them for 2 fun facts, and yours are particularly funny. So the first one is you're very bad at giving directions, so that your friends would call you first when they're lost, just to ask for like rubbish directions. I'm assuming. And the second one is so you host this thing called Beers with Engineers, and you also live in Germany. But it turns out you actually don't like beers. So I found that to be hilarious.
Yes, fun facts about me. Yeah, I even if I'm in Bayern, like it's where the Oktoberfest is also happening. It's just a no-go for me. I don't know. I couldn't get used to it. I really don't like the taste. But yeah, I'm up for anything different than beer, but no beer. But in Beers with Engineers, everyone is free to choose whatever they are drinking. So we are not forcing anyone for specific drinks.
Yeah, I get that. I don't drink either, and I'm assuming it's like Beers with Engineers, and there's Ekin. So I thought it was funny. And okay, so before we start, let's just address the elephant in the room right now. So this morning, are you like a millionaire right now?
Man, I wish. Everyone wishes that. But yeah, that's not something that I can comment on.
Yeah, I know that. I'm just making a silly joke. I warned you about this. But okay, so today we're here to talk about this white paper that you actually co-authored, I think, with Run AI, and it's about different ways to serve LLMs. And this is something that I don't see a lot of people talk about because most of the stuff that we use in production is kind of hidden behind an API layer. So we're like, yeah, we're behind the scenes. So today we get to pick your brain. So I know you have some stuff prepared, some slides maybe.
There are a lot of people using APIs and basically letting others host the LLMs. But what we see is when things get scaled up, the costs are also increasing. So you need to figure out a way to host your own LLM, or that might be also a data privacy issue. Like it's so natural for corporations not to want to send the data to some other companies. So as you said, there is not much of an information how to choose these techniques or like tools, what to pay attention to, what actually is your use case, if it differs from use case to use case. So what we did is, okay, let's gather all of the current tools and techniques and throw them to the wall and check how they're actually performing in different scenarios, in a little bit of a production scenarios, and see the performance benchmarkings. So we also published the GitHub repo for that. And you can basically use the GitHub repo if you want to benchmark anything else at any tool, etc. So I will give the QR code for that. So yeah, you already introduced me, but a quick outline from my side as well. I'm a data scientist at Run AI. I'm based in Munich right now. I'm also running an infrastructure club, which is another Discord server. You can scan the code. We also have an open source project going on with Run AI. So if you are working in a small data science team and you want to share your GPUs more optimally, you can check this out. It's a very cool tool, and we are still working on it actively. So feel free to ping us if you have any feature requests, if you need some support, etc. We also started supporting Ollama. And as you also said, hi, I'm still curious about distributed training, also inference right now. I'm thinking about Rust in AI, so I started reading through a little bit, but I'm still skeptical, and of course, federated learning. So yeah, let's go back to the topic, LLM serving benchmarking. So this is the QR code to the white paper if you want to read it through, but I will give you an overview right now. There is also a link to the GitHub repo on white paper if you want to check it out. So in this white paper, we used a single A100 GPU, which had 40 gigs of memory. As models, we use multiple models. I will also mention those models while showing you some experiment results. So we all used llama models. One was 7 billion, the other one was 7 billion chat and 13 billion chat. Tools and frameworks, we chose some popular tools and frameworks, but of course there are like more out there. We just needed to, also give some specifics to ourselves. So the first one is TensorRT LLM, and of course Triton inference server. Both of them are by NVIDIA. The other one is VLLM, which started as an open source project / paper, whatever you call it. Now it's quite liked by the community. There is the Ray LLM with VLLM engine, TensorRT LLM, I already said, and TGI. So TGI is also by Hugging Face. And as data set, we created something, but we also used ShareGPT, which is openly accessible in Hugging Face. So before we jump in, I want to give you an overview of what actually is a crucial component of LLM serving, because that's not trivial for us. So there are two main components. One is engine and the other one is server. So the server handles all the HTTP and gRPC requests coming in from many different users. And it kind of provides a logic for queuing, managing the engine, sometimes even multiple engines. And here we also measure latency, throughput, etc., like those metrics that you care about. And on the other hand, we have the engine. That's the actual component that runs the models, and it's responsible for generating the tokens. Basically, it handles every aspect of the generation process, also including like batching those requests that are coming from the server, and it typically has a lot of optimization going under its belt. So this is a quick overview of all of the components that you should know before we jump into the experiments. And now it's the fun part, the experiments. So first of all, I will talk a little bit about the sweet spot of batch sizes on engines. Then VLLM's edge by using KV cache preemption. Then I will talk a little bit about what happens when you know your output length ahead of time. The fourth one is, I think, in my opinion, is the most important one, which is the complexities of memory management in serving LLMs. And finally, some advice on choosing a great server engine combination and how it differs in comparison to other experiments. Okay, so First of all, current tool options. What are those tools? Which ones are the engines? Which ones are the servers? So first of all, we have two servers from the tools that I showed you before, TensorRT LLM and VLLM. And we have two servers, Ray LLM and Triton's inference server. We did the experiments of Ray LLM with VLLM engine, but you can also use TensorRT LLM. I think they started supporting that, but we need to check. And we did the experiments of Triton with TensorRT LLM engine. And in comparison to others, TGI is a little bit different because it's like engine and a server. So we put that in another category. So yeah, this is basically the overview of what we use for these experiments. One important thing I want to mention is the policies that you see, the KV cache management policy. So if you're not sure what KV cache is and why it's important, we also have a blog post in our website. Feel free to check it out. But here, TRT LLM provides a reservation, while VLLM provides a preemption policy. So you can think of them like static and dynamic. Reservation policy differs from preemption by allocating some sort of necessary resources ahead of time to avoid KV cache eviction. So, but how is this done? It predicts the KV cache size needed for a given input length and reserves the memory on the GPU in advance. But of course, like if you are doing that, you need to make sure that it's carefully calibrated to optimize the memory utilization, because it's very easy to underutilize the GPU. And the other one is the preemption mechanism, which VLLM is using. It's a technique when system capacity is overwhelmed with requests. So when the GPU cache becomes saturated with KV cache of user requests coming in, the system decides which blocks to evict to make room for the new ones. So the engine, which is VLLM in this case, starts evicting some of the already handled requests. So there are different types of eviction techniques as well, such as swapping, copying the cache from GPU memory to CPU memory, or recomputation of KV cache when needed. Yeah, this is the QR code to the blog, the other blog that I mentioned. If you are not sure what KV cache, etc. is and why it's important, feel free to check it out. Okay, the fun part. That's the second fun part. So now we are set for the experiment results. If you want, we can also do a round of questions if there is any, or you can just let me know when we are doing it. Are we doing that at the end?
Yeah, one question. Well, quick question.
Yes.
So when you did your experiments, I read through like the white paper. There were some considerations between like throughput versus latency, right? Sometimes a lot of throughput is better. Sometimes latency is more important. So like in which scenario is throughput more important than latency, and which one is the other way around?
It depends on your use case, right? Like sometimes, like for us in this white paper, we put more emphasis on throughput because like for us, we wanted to see how much processing we can push through the GPU and all of the user requests like as batches. So for us, latency was not the main focus, but of course, if you are I don't know, creating some sort of a chat bot, etc., latency will also be an issue. But yeah, it's also not something that you should think separately, right? So they are not they are not completely different metrics, and they will probably affect each other. So I think the most important part is take your use case, take all of these tools, and actually push the limits, check out how it looks when you get a lot of requests, and actually choose your tools like that. So that's what we also learned. You just need to try it out, not in the production level, but take it in-house and push the limits, see how they are performing, because you might actually find out something that you didn't even expect. So I would say it's very dependent on the use case. Yeah, that would be my answer. I hope it answers the question. It's a little bit vague, but that's what we learned. You need to be open to surprises.
Yeah, everything depends on like the circumstances and use case, and there's no free lunch basically, so you can't like have both.
Yeah, exactly. Unfortunately, like you can't even know how long the sequence is gonna be, you know, from the users. I will also talk about that, and that actually affects the whole balance in the throughput even. That's also the case for latency. So yeah, there's no free lunch.
Cool. Just one more quick question. So on the components of LLM serving diagram, there's a part there. There were two parts that I didn't understand. So which one? The first one is multi-model management, and the second one is model registry. These are the two things I've never seen before in my life. So can you like just touch on them just briefly?
So the engine can actually manage, like, use multiple models. So the server can host multiple models within the server, and you might also have a model registry, which can be some sort of a data volume, and you can use that data volume where you store your model weights to manage those models in production. It's for companies or organizations that want to serve multiple models in production.
Okay, that makes sense. That's like way bigger than my scale. So probably not useful information for now, but maybe in the future.
That's what happens if you are working with enterprise.
Yeah.
You just need to be open to a huge scale, which is sometimes like mind-blowing, trust me.
Cool. Anyone else have questions? If not, we can just continue. If you do have questions, just unmute yourself and say something.
Yeah.
If not, you can just continue.
Okay, I will. Thank you. Okay, so here a huge kudos to our CTO office. So this is a teamwork basically that I will present. So okay, let's jump into the first experiment where we checked out throughput dynamics of VLLM and TRT LLM with different query per request rates and batch sizes. So what we wanted to understand is how these engines handle batching under a heavy load of user requests using a fixed input-output sequence length. So we know the input-output sequence length. We know how much tokens will be generated for each user, and we are getting a lot of requests from the users. Okay, so we realized a pattern, as you can see now. Both engines have a throughput peak for a specific batch size. So batch size is batch size, and the top parts are, like the columns are different QPS rates. And they have a specific batch size that they perform best. Like for VLLM, it's 192. For TRT LLM, it's 128. So if you ever want to do something with these engines, I would suggest you to check out this experiment with your own setting to figure out the optimal batch size. But we questioned later on, okay, but why is this the case? So this led us to the next experiment, which is basically the experiment of preemptions. So as I said, we know that VLLM is strategically preempts the KV cache, and we thought that this might actually contribute to this behavior. And spoiler alert, drum rolls, it does. So to investigate it, since VLLM is open source, we modified the VLLM code a little bit and basically counted the number of preemption actions that are taken by the engine, dependent on the batch size of users. So you can see it on the x-axis. And a little side note, since TRT-LM is not fully open source, we couldn't investigate it further. They claim that they don't have preemptions implemented, but they have the similar behavior as you saw in the previous experiment. We don't have much clue what is going on under the hood. If anyone knows here, please feel free to share with us what is going on actually. But yeah, so what we did here with VLLM is we created a backlog of requests, a lot of requests for different batch sizes, which starts from 128 till 288. And we sent like 64 QPS per second. That doesn't matter because we just wanted to create that backlog. And the preemptions started occurring at the magical batch size of 192, which was the same peak throughput that you saw. So the key takeaway is that preemption does affect the throughput, but as we will see later on, this benefits us a lot when we're operating in a memory bound regime. Next one, since all the memory need to be calculated upfront for some engines which are using reservation policy. So if you know the output length, preemption is not a killer feature. That's what we realized in this experiment. So here we are again measuring the throughput. This time we also added the RayLLM and Triton with TRT-LLM engine to the whole discussion. We know input sequence length, we know output sequence length. So as you can see, if you know all of the parameters, actually, it doesn't matter which engine you are using. Like VLLM, TRT-LLM, I will also count TGI as engine for now. They act similarly. What is important is right now we see that RayLLM and Triton with TRT-LLM has slightly lower throughput, which we will come later on. But that showed us that it might be the case that servers are adding a little bit of overhead on top of the engines, but in a production level use case, you just need a server, so you can't run away from it. So yeah, keep in mind that this is a very naive scenario because we know everything, right? But real-world scenarios are so tricky with a lot of parameters. You can't know how much text you are going to receive to your server from a specific user. So now we decided to increase the complexity a little bit by turning the output sequence length into an unknown and restricting the memory allocation for KB cache in the next experiment. So before diving into the next experiment, let me explain this a little bit. So with all of these unknowns, the next experiment will be the most interesting one. So first of all, we don't have unlimited memory on GPUs. I wish we had, but we don't, unfortunately. So we need to manage the memory that we have well. And LLMs are so large nowadays that we are not compute, but memory bound most of the times. So we have two main components when it comes to memory consumption in inferencing, model parameters and the KB cache. So model parameters are there, like they allocate static memory on GPU. We need them on GPU. And the KB cache is dynamically expands and shrinks based on the number of requests that are coming in into your system, plus the sequence length, as I mentioned. And this makes all the memory management very tricky because you have something dynamic as well. And especially in the multi-GPU case, there are some crazy tricks you can do. But looking at each engine already creates large differences depending on how they choose to manage this whole memory. And at this point, model choice also starts to matter a lot. So I don't know if you guys ever played models like 7 billion and 7 billion chat, like basically the chat models and the other models. The 7 billion one, it's quite verbose, and it generates relatively long output sequences until it hits the end of sequence token. And the chat model, on the other hand, generates relatively short output sequences until it hits the EOS. So we will see how this matters in a second. So here, we created this experiment to check out the most about memory management. This is a little bit of a complicated experiment, so I will go slowly. So first of all, we limited the GPU memory used for KV cache. In other words, we used fractions of the GPU memory and checked how the engines performed within that constraint. So the model parameters took approximately 15 gigs of memory. We are using the model in half precision on the GPU. So the rest of the memory is used for KV cache, and in the x-axis, you are seeing the GPU memory that has been used in total. So model parameters plus the KV cache that the engine can use. As I said, for this experiment, we didn't specify the output sequence length to engines and let the models actually decide when to stop a sequence. So we are waiting for end of sequence token. So what are the results? Let's have a look. First things first, we see consistently improved throughput as we increase the memory. So far, so good. That's, I think, trivial at this point. When we have a look at the graph very carefully, when we use Llama 2 7 billion model, not the chat model, VLLM has a slightly better throughput performance than TGR across all GPU memory fractions. Not the dashed ones, basically the other ones. And when we transition into the chat scenario, basically the dashed ones, we see a notable difference now in throughput performance between TGI and VLLM. Here, VLLM outperforms TGI across all fractional memory allocations for KV cache. And interestingly, when we restrict the memory for the KV cache to even, I think it does 17 gigs, so 15 gigs for model parameters plus 2.7 gigs or something like that for KV cache using VLLM. So it's the very left part of the figure. VLLM performs better than the chat model is used, which is generating the end of sequence token before the Llama 2 7 billion. So now, when we move on to the TRT LLM, TensorRT LLM, with both models, we see almost no difference in throughput and memory consumption. It's basically the same. And while it performs nearly similar with VLLM chat, when available GPU memory is higher, basically on the very right side of the graph, TensorRT LLM actually underperforms compared to both engines when we use lower KV cache memory. Something that hints at the preemption VLLM use case, to be honest. And under these conditions of reduced memory, we even got out of memory messages from TRT LLM, so we couldn't even measure the throughput. So this experiment then led us think the next question: what happens when we stress the memory requirement, this time with a bigger model, not with KV cache, but using a bigger Llama model? This will also leave a small amount of memory to KV cache, basically in comparison to using a smaller model. So would that change anything in the dynamics? It turns out it does, but not in a way that we expected it to be. So that's why you need to try out with these tools. So it's very obvious that the throughput would decrease in comparison to using Llama 7 billion, because as I said, like, we have way smaller GPU memory available. So what was unexpected though is that the VLLM is, of course, again, best performing one. It's followed by TensorRT LLM with Triton inference server, and after that we have VLLM with Ray LLM for higher query rates. This is something very interesting, because if you remember the second or the third experiment, the model was lighter and the output sequence length was known, and the servers were just adding overhead to the engines. So the throughput was lower when you use engines together with a server. So the server selection actually matters and might enhance the performance of the engine. Obviously, we are not exactly sure why that is. It was out of the scope of that benchmarking. So we need to investigate this further. But that's something that we found also interesting and wanted to share with the community. Yes, before I jump into the overall key takeaways, do you have any questions?
I do have one question. So you mentioned potentially limiting the amount of memory available to the KV cache and giving it to the model's parameters. Is that right?
Like KV cache and yeah, like for this one, you mean?
Yeah. So
yeah.
we're in like a real world scenario. If you were to do that, would there be any sort of like trade-offs in terms of, because you get better throughput, but then do you have any trade-offs in terms of like performance there? If you just give more, yeah. So if you give more memory to KV cache, is there anything weird that would happen?
So the thing is, if the throughput will decrease if you have the same amount of memory in total, but you have a bigger model. So the throughput will decrease in comparison to using a smaller model, right? So here, for example, with VLLM, we see around, let's say, 500 something, but here it's basically exploding. This is the 7 billion use case, and this one is the 13 billion use case, right? So the throughput will definitely decrease because you don't have that much of a memory available for your KV cache, and you can't basically process those requests coming in as fast as the previous use case. I think that's something that needs to be thought through. But yeah, like at the same time, you are using a bigger model, so that might be a very huge plus for some specific use case, because you fine-tune 7 billion model, but it's not performing well, and 13 billion model seems to be performing way better than the 7 billion one. So it's, again, it differs whatever model you are using a little bit. So it's a trade-off issue. Yeah, does that answer the question?
Yeah, I think what I learned from this is that depending on the use case, again, you have a couple of levers that you can pull, and given like, it's like almost like an equation. So given like the model size and this inference like server or whatever, you can kind of like push and pull a certain way so that you get the best performance for your exact use case, but then it wouldn't work for like a bigger model. So yeah, that's really cool. It's just one option in case somebody runs into this.
Yeah, exactly. Yeah, okay. So key takeaways, the stuff that I want you to think after this session, while you are cooking, while you are taking a shower, I don't care. The learnings that you should take after watching this or hearing this. So let's have a look. First of all, use strategic preemptions. As you saw, VLLM seems to be performing super well if you don't know a lot of parameters, which in most of the cases you will not, because you don't know how many users you will host, you don't know what kind of sequence you're going to get to your server. Preemptions are the key to find the sweet spot between memory optimization and computational efficiency in model serving. The second key takeaway is you should ask yourself if you have any insight on sequence length. So do you know how long the sequence are going to be, or do you want to make that set? Because TensorRT LLM and TGI allocate memory on the GPU based on the expected KV cache size for upcoming batch sizes and sequence lengths due to this all reservation policy that we talked about. And if the output sequence length is not known, an engine with preemptions might be more suitable for your use case. Otherwise, if you know everything, it doesn't matter much. And model size has an impact, as we talked, because we are running these models in memory-bound regime most of the times. And the larger models just shift the curve that we saw in the memory management slide to the left, basically. So we operate on the very left side of the memory-bound regime, and here in memory-bound regime, more GPU memory also means more throughput until the model becomes compute-bound. Then you will have to look into model parallelism techniques using multiple GPUs to host that model. And fourth, the surprising one is servant selection matters. So you can actually improve the throughput, as we saw in the last experiment. This is open for further investigation. If anyone from the YouTube audience listen to this and knows exactly what is going on or have ideas, have experience, please reach out to me because I'm curious. And last but not least, I want to add a bonus key takeaway from our next benchmarkings with parallelism, model parallelism on throughput. So we saw that the throughput stabilizes with higher QPS rates, right? Because it enters the compute-bound regime. So in the further experiment batch, we used the parallelism to overcome this challenge. I also dropped the QR code if you want to scan it. It's also in the website, so you can have a look. So we used tensor parallelism, and we realized that we could increase the throughput per GPU by 57% for VLLM and 80% for TensorRT LLM, while we also see impressive performance improvements with latency. So these are the per GPU increases for throughput. So this made us realize that multi-GPU inference setups should not only considered when the model doesn't fit into a single GPU, but also for reducing the latency and in the memory-bound regime for increasing the throughput. So if you're interested, feel free to scan the QR code and have a look at there as well. So yeah, I think that was it from my side.
I do have a question, and I'm really curious about like your take. This is more like future bounded, I feel like. What's your opinion on Grok's LPU inference engine?
Very impressive results. I would say I was very impressed when I first read their documents. It's all about the scale, right? Like later on, I realized that they used how many instances to get those results. It was a lot of chips actually being used in parallel. So can you scale that up? Then it's amazing. If you can't, then of course it's gonna be hard. You know, if I need to get, I don't know how many it was. Let's say 1,000 chips from Grok to run a couple of LLMs. If like, can they even provide that to me, that amount of chips? If so, it looks very promising, but yeah, I don't have much information about how it works. If you can even purchase that amount for now, it's probably not. It's still in the research phase probably. The results look amazing, but again, like we need to see the chips. We need to see how much we can get the chips. Then that's gonna be a topic that we can discuss further. But yeah, like it's insane amount of chips that they were using for those results in the paper.
Yeah, because my buddies and I were just having this conversation about, oh, should we switch all our entire stack over to Grok? And then I'm like, this is too good to be true. Something's off here. And then I did some, and then recently Llama 3 came out, and it got really popular. Like the Grok plus Llama 3, 7B and even 70B, 8B and 70B was like really fast. People comparing to GPT-4, and then turns out they were rate limiting a bunch of people because they didn't have enough capabilities there. So
Yeah,
like you said,
you just need to wait. Some bold people from the community to check it out, crash it to the wall, and see what is actually going wrong, and then you can make your own decisions. Like when TRT LLM first launched, I was also like going to events in Munich. I chatted with some people who are basically serving multiple models to their users. And I asked like their opinion about TRT LLM. It was the first week that it got released by NVIDIA. And she was like, yeah, like, let me see what goes wrong with the users that are going to adopt it first. Right now, VLLM works for us. So if something is super cool, I will change it. If not, then we will see what is going on. So you should always wait a little bit until you really see what is going on under the hood and what are the feedbacks of the whole community. That's why I love this open source community. Like everyone is trying it out, just basically crashing that to the wall, and then we gather all of the learnings and move on. So yeah,
I'm gonna steal that phrase from now. Crush the engine to the wall.
Yeah, just throw it to the wall, see what happens. Yeah,
that makes sense.
Experimentation.
Okay, so one last question. What's like the most exciting thing for you right now? Like, what do you think is the most exciting thing that you're waiting for?
In general, or in the LLM serving use cases?
Either, whichever one's more exciting.
Okay, so like the LLM serving is still not solved problem in my opinion, because like there is a lot of problems to solve. Like model loading is a huge issue. If you want to optimize the cost of serving a model, you need to scale it down and scale it up very fast, which is very hard when you have a huge model. Like you need to do a lot of optimization, and there is not a single tool that solves everything. So it's still an open topic. I think we will see a lot of projects from the community, from companies that tries to solve it. So I'm excited for that, because you can't send API requests to other companies forever, right? Like if you are going big and if you are scaling up, which at some point the machine learning projects will get mature about, then at that point you need to have some in-house solution that is growing up to basically handle those requests in-house and way cheaper. So I think we will see that, and I'm very excited about seeing those kind of solutions. So that's one thing that I am excited about. The other one is robotics, like reinforcement learning. I'm not coming from that field, but I find it amazing that right now people are also trying to use LLMs in reinforcement learning and leverage those, which I find interesting and super cool. And I feel like it might be growing faster in the future. So I'm very excited about the all research that will come up from that area as well. So yeah, I think these two are my my biggest topics that I find very interesting for the future. What about you? I will just redirect the question.
Okay. How the turntables. I agree with you. I think robotics is super interesting, and being able to control computers using like natural language is also something that I was kind of a skeptic before, but I've seen like different people doing it. Like for example, the open interpreter folks, and I'm like, wow, like this is happening. Like, what a time to be alive. And robotics as well. I don't know if you've seen like the new Boston Dynamic reveal video of like the exorcist robot that's like
Yeah,
faster, and it just like turns around and then, like get right up in your face.
yeah.
I like that.
I couldn't parse it. Like my brain was so confused when I first saw the video. It's amazing.
And I think another one from Figure where like the person was just telling the robot to like pick up apples and bananas, and it'll just like do LLM inference in its own head or something. So I don't know. I feel like we should get you on maybe a couple months from now or something. Something's gonna come out, and I feel like you're gonna do some experimentation. So we would love to have you on again.
Thank you very much. I will keep you updated if we throw something to the wall again.
Yeah.
Yeah.
Throw it against the wall, crash it. Open invitation to Ottawa in case you ever stop by Canada.
Open invitation to Munich as well. Feel free to hit me up if you come over. We can get some beer. I'm not gonna drink beer, but you can drink good German beer. I will just get my wine.
I'll get like a fake mojito or something. I don't drink either, so.
True. You're not drinking. Yeah.
All right.
Can get
that's it.
Free.
That's a webinar. Thanks, everybody.
Thank you, everyone.
Thank you very much. Thanks.